was supposed to do it all yesterday, my streaming, but I got busy, so we're gonna do it today. Is this working? Alright, I was supposed to do it all yesterday. Okay, it's working. Yeah, I was supposed to finish the medium playlist yesterday, but I just got busy, so we're gonna do it today. This block, we're just gonna do these two. So, Leetcode. Add two numbers. Oh, it's the second problem they ever made. Okay. Not negative. They're stored in reverse order. Add these numbers and return the sum as a linked list. You could just convert them to numbers and add them, but since they're like back to front, you could just add them plus add the carry on. So int carry is equal to 0 while L1 is not equal to null and L2 not equal to null. List node, new list node. We could just use one of the existing ones to act as the head, but I feel like this one is more clear because using L1 as the head implicitly doesn't really make sense. So we could just declare new nodes as we go. Yeah. So we're just creating new nodes. If there was a space constraint, what you would do would be L1.val is equal to L1.val plus L. You want to set L1.next equal to L2, which is the current position of L2. And then we have a dummy head going to L1.start. Honestly, let's do this solution. Why are we going to do this solution? Because this solution doesn't need you to allocate any more space for linked list. So this is like a more advanced solution. Like, unless the recruiter tells you, hey, we have a space constraint, don't do this. Because why would you make the interview harder than it is? They're just like trying to see if you meet a checkbox. If you meet that checkbox, you're good. They don't care if you meet the checkbox better or worse. But just to make it more interesting, just to make the problem more interesting, I'm gonna do it the harder way. L1. Okay, L1.val is equal to L1.val plus L2.val plus carry is equal to, carry is now equal to L1.val minus 10. Is it minus 10? Oh, divide by 10. Always gonna be like 1. And L1.val mod 10. While L1.next is not equal to null. And, yep. Okay. So we continue this process of updating the carry and the L1. L1 is equal to L1.next. So, if L2 is not equal to null, actually, and now we do a while L2 is not equal to null. So over here we can set L1.next is equal to L2. So L2 is either null or some value. And now we do L2.val is equal to L2.val plus carry is equal to, actually L1, we can move this up. L1 is equal to L1.next, and then we can actually just repeat this for loop, but just with L1. because now L2 is connected to the end of L1. We don't have to really think about L2. We just have to worry about the carry. Yeah, that's it. And then we could return head.next, which is a dummy head. It's not the actual head. This just points to the start. Let's see if that works. Output 793564. Oh, and L2 is equal to L2.next, of course. Now run this. Because L local is null. L1 is not equals to null, so this could be null here. And actually, do we not care about L1.next? No, we just care if L1 is not null. Just add the carry and then keep on going. 7, 0, and then 3 and 5. So 7, 0, 3. It took 3. It should add 4 as well. Oh, so here L1.next was equal to null. So I see. Shoot. And I did L1.next is equal to L2. So why don't we add an if case? If L1.next is double equal null. Shoot. This is where it gets confusing now. Because what I'm doing is I'm saying 2, 4, adding these, then I see 3, but 3.next is null. So should you even attach it to the next one? No, you should add these two first. And then if L2 is not equal to null, then set L1.next equal to whatever. So why don't we have L1.next there. So in this case, when the next value is null, when the next value is null, it stops there. It still adds it, but stops there. And then it moves this over, so it should be fine now. Because it stops there, it still adds. Nah, that's not right either. It's not right either. Okay, so and L2 is not equal. No, L1.next 2.next is not equal now. Okay, so this will go to all the items except for the last. And now we have an if case here. So if L1.next, L1 is not equal to null, and L2 is not equal to null. Actually here, because we want to add it either way, if L1.next is double equal to null, we should break. Do we still increment L2 though? Yeah, because we already added L2, so always increment L2. So break, in this case, we may want to attach L1 to L2. Okay, and then if L2 is not equal to null, you do this logic, which is attach L1 to L2, move it over, and then keep on continuing adding the carry. Oh, but it's the same thing, because what if the carry is not null? So while L1.next is not equal to null, L1.next double equal null, then break. May want to attach carry. Yeah. And you say if carry is not equal to, and then here at the end you say if carry is not equal to 0, then L1.next is equal to new list node carry. Dude, see, look how much more complex the code got, because you're not making new stuff. Yeah, see, look at me getting cooked right now. This is an easy question, but when you like add pointers, you gotta protect it, so you can't go to L1.next because that'll be null. So you have to stop here. See, if we return dummy head.next here, we just comment out the rest of this. What is the state we're at? Yeah, so we're at 703. So if L2 is not equal to null, L1.val is equal to I don't know where to just add this. L2 is equal to null. Actually, why don't we do an OR? Actually, maybe we can handle it all in one case right here, so we don't have to add all this extra code. So if L1.next is null, we still gotta add everything. L1 is equal to L1.next, which is 3. Yeah, let's just run this, see what we get. We probably get 703 here. 703 L1.val plus, nah, this is a real problem. So we just said the correct answer for the first one. But then you gotta think about the cases. So what is edge case 1? Edge case 1. L1 is longer than L2. So make this an OR. And let's do int sum is equal to 0 if not equal to, yours at L1. So L1.val. If L2 is not equal to null, L2 sum plus equals L2.val 2 0 L2.next. If carry is, oh yeah, I was at carry 2. Carry carry is equal to sum mod 10 sum mod 10 L1.val is equal to sum divided by 10. So in the case we have so we added everything L2, L1 or L2. So L2 is longer than L1. What do we want to do? So if L1.next is double equal to null and L2 is not equal to null, it's because we already do L2.next here. Then what do we want to do? We want to set L1.next is equal to L2, and then we can do L1 is equal to L1.next. And then at the end, if carry is greater than 0, L1.next is equal to new list node, And then, actually, no, let's do else if L1.next is double equal to null and carry is greater than 0. L1.next equal to new list node. Carry L1 and 0 to L1.next. Yeah, that's pretty good. This is divide by 10. This is mod 10. Bro, so just make a new list node next time. You know, don't do this logic. This is so annoying. If L2.val L2 is equal to L2.next. If L2 is not equal to null, run. Oh, that's what I meant. Is it infinite while loop? Oh yeah. Always move up. Yeah, so we're able to do this with no added space. But look how much more complex it was. And it doesn't even work. 2, 4, 9, 7, 10, 9, 4 is 15. Oh, 14, 9, 4, 14. 9 should have added carry. Carry is equal to 0 here. Okay, 704. So 4. This is the first carry. 7. No. This is the first carry. 4 because it carried over again. 9 plus 1. So this was 7, 4, 9. So plus equal to L2 dot pal. L2 is equal to L2 dot next. Sum plus equals carry. Yeah, it's interesting. Let's do a test case. Yeah, always write the simplest code you can. There's no space constraints. Don't worry about it. This shouldn't be that hard though. I don't know why I'm messing up. Let's see each time system.out.println. Sum is, well, actually we know what the sum is. It's what's added. Let's say, see, yeah, sure. Sum is whatever. Carry is carry. Yeah, sure. Let's run it. Sum is 7, carry is 0. Sum is 10, carry is 1. Sum is 14, carry is 1. Sum is 19. 19? How does it get 19? Carry is sum divided by 10. 14. Sum is 19. So this is which case? And L2 is not equal to null. L1.next is equal to L2. Oh, do you know why? And now we have to set L2 equal to. Now, so when we attach this, ignore L2 now. So when we attach L1 to L2, we don't want to look at L2 anymore because that's just a part of L1. Interesting. So it was 9 plus 9 plus 1, which was 19. Okay, so it's accepted. We didn't use any extra space. Yeah, look at this. This is ridiculous in this. Look at this. You remove a print line, suddenly your runtime goes from 38 to 1 milliseconds. It's crazy. It's crazy. Now I have the best solution. I had one of the worst before. But this is like such an easy problem if you don't like do these edge cases with L1 and L2. But it's good practice. Good practice. Odd, even, linked list. Damn, that took me 20 minutes. I'm cooked. Alright, given the head of a singly, group all the nodes with odd indices together, followed by the nodes, we return the reordered list. Okay, so we have 1, 2, 3, 4, 5. So with list nodes, you can't go back, or any linked list, you can't go back, so you need to keep references to each of these heads. So we need a reference to, let's say list node odd head is equal to head. New list node odd head dot next is equal to head. So we have a pointer to the odd head and the even head. Head dot next. So if head is equal to null, or head dot next, or head dot next is equal to null, then we could just return head, right? Because it starts with whatever the first value is. Yep. Okay, so now we have our odd head and our even head. This one points to 1. This one points to 2. Yeah. So what do we need to do? Now we need iterators. So list node odd iter is equal to head node even iter is equal to head dot next. So while odd iter is not equal to null, then we can set even iter equal to head odd iter dot next. No. While, because even iter is after odd iter, and this is before even iter. So while even iter is not equal to null, we could set even iter is equal to, or odd iter is equal to even iter dot next. Odd iter dot next. So for this example, let's just look at this one. Oh, and you're like, Father, why are you coding in the comments? I have faith in my, Java abilities. I can just like write this. And once I plug it in, it'll work. Faith. Not, see. Okay, so 1 points to 2. So we have odd iter is here and even iter is here. So odd iter dot next. So let's do odd and let's do even. So odd iter dot next is equal to even iter dot next, which is 3. Then even iter dot next is equal to odd iter dot next, because now this iter is equal to odd iter dot next. So now this is, we connect it to 3 and we move it over. So this connects to 3 and we move it over. And now even iter dot next is equal to odd iter dot next, and we continue this process while even iter dot next, or even iter is not equal to null, or even iter dot next is not equal to null. Why? Because we never want something, we don't want the end of our odd iter to be pointing to null. No, we don't want odd iter to be null. So what I mean that is, we go this connects to this, 2 connects to 4, 3 connects to 5, 4 connects to null. But we don't want 5. Actually no, so while even iter is not equal to null, because now we have odd iter at 5, we want odd iter to connect to the start of it. So after this, we want odd iter dot next is equal to even head dot next, because it's even head dot next points to the start of odd iter, no, even linked list, and return odd head dot next. Ooh, do we throw it in? Do we throw it in? Am I like that? Am I like that? Yo, I'm like that? Shoot. Yo, am I like that though? Oh my god, a semicolon. Okay, these don't count as issues. Okay. Oh yeah, so we do want dot next not equal to null, because we do move it forward at the same time. 1 3 4 5 2 5 2 4. Okay, well actually won't, because I'm not like that. So let's look where we're connecting. We have odd head and we have even head. So odd head dot next is equal to the head and head dot next. Odd iter dot next is equal to even iter dot next. So odd iter is equal to odd iter dot next. Val dot print line odd iter dot val. 1 3 4 5 2. So 1 connects to 3, yeah, and then 2 connects to 4. Oh my god, even iter is equal to even iter dot next. Dude, what the heck? I forget that. Basic. And then I think yeah, okay, we can keep this null because it'll say, hey, we're at 4. Move this up to 5. So move up to 5. Now 5 points to null, and now we're good again. Hell yeah. Because locale 4 is null. 1 2 3 4 5 6 7 8. Wait. Cannot read field next because locale 4 is null. Alright, let's run through this example real quick. So this starts at 2. So we go, let's start here. We're at 1 and 2. 2 points to 2. So it goes, hey, I want to see it equal to odd iter dot next 3. Now we're at 3, this points to 4. Now we're at 4, this points to 5. This points to 6. This points to 7. This points to 8. This points to. But over here, and even iter dot next is not equal to null. So we don't want to ever set never set even auditor to null. Yeah, that's the problem because we set this to null next. We set this over to null. This tries to get null out next, it breaks. Okay, so walk through an example. It will help. Intersection. Oh yeah, okay, easy peasy. Node where they both intersect. Now you can have a hash set of like list node objects, but that's just their memory address, right? So I'm going to show you why a string is fine. So while head A is not equal to null, scene.add head A to string head A is equal to head A dot next. Now while head B is not equal to null, actually it does want you to return the list node, so this does have to be an object of list nodes. Yeah. See, it's so weird. They mix up the easy and the medium questions because the easy question should be in the easy playlist, but here we have an easy question in the medium playlist. Alright, trees and graphs. Bro, I swear I've already done this problem. In order traversal? Or something like this. Given the root of... Oh, in order traversal. Okay. Recursive solution is trivial. Can you do it iteratively? Let's do recursive first, just to show how trivial it is. What is that in order traversal? I think it's like root, left, right. Root, left subtree, right subtree, left subtree. Root, left subtree. Left root right. I think it's left root right. So leftmost value, then go to the root value, then the right value. So left value, left value, right value. So if we see like a tree, we could draw one out real quick. 1, 2, 3, So an in order traversal would be like go to the leftmost value 4, 2, 5, 1, 3, 1, 6, 3, 7, 1. Yeah, I think that's right. Let's see. 1, 2. No. 4, 2, 6, 5, 6, which is the leftmost. So 4, 2, and then it goes all the way to the leftmost value. 5, 6, 5, 7. So it runs down this tree, and it's like, hey, don't go to this node. Go to the leftmost node. 6, 5, 7. Then 6, 5, 7, 1. So it goes to parent node 3 because there's no left subtree, but it goes to a right subtree. Goes to leftmost value 9, 8. All right, so that's an order traversal. Root.val. If root is double equal to null, return. You want to do this as output. So output.add root.val, but only after you do the in order traversal of the left subtree. And then after that, you can have the privilege of doing the right subtree. And now we just need to declare our output. And traversal of root and output. Okay. What? Okay, so that's the trivial recursive solution. Now let's do the iterative solution. And for the iterative solution, we gotta think what's the best way to do this. Description in order traversal. So 1, 2, 3, 4, 5. So any of these problems, I'm gonna tell you straight up, any of these problems, you gotta see, you're gonna have some data type you're pushing into and you're popping out of. So what do we have? We usually have like a queue or a stack or like some array, like a list. We gotta say based on the type of data structure, well, based on the type of traversal, which makes sense. Makes sense. Okay. Let's copy this. In order trav hitter. Okay. So a good idea would be first off, let's see. While root dot. So while this root has a left subtree, go explore the left subtree. So go explore the left subtree to maximum depth. So if we see 1, go to root.left, which is what? 2, which you could then go to root.left, which is 3, or no, which is 4. And then we can't add any more, right? And then the first value we want to see is what? The first value we want to see is 4. So first value we want to see 4. But if we're pushing into it and we want to see the last value, last in, first out, we want a stack of values. Okay, so we'll start with that. Let's have we have our output list and we have a stack of tree node. Root is a new stack. Okay, So while the stack isn't empty, we have something to do. So while the stack that is empty, because so say after we pop out 4 and we get to 2, right? We have to add the right subtree. So we have to have some logic that after we add in the leftmost value, the value we're looking at, we have to explore the right subtree. So we can use a stack for that. So pop out 4, explore the right subtree if it exists. Then pop out 2, explore the right subtree if it exists. Pop out 1, explore the left subtree if it exists. So right away in the stack, we could do something like while root is not equal to null, stack dot push root is equal to root dot left. Then the current value is equal to stack dot pop. Then we can add this value to our list. So output dot add root dot val, because we'll never add null. Root dot left, root is not equal to null, and yeah, okay, that's fine. But then we could reuse the root, because after we add in all the left values, we pop out a value. So say we add in 4 and we don't explore the right subtree because it doesn't exist. Then we pop out 2 and we want to explore the right subtree, right? So the second part of this problem is just saying root is equal to root dot right. So this now explores the right subtree. So it'll go say, hey, we saw 4, now we saw 2, set it equal to 5, the next value that we're looking at. So if 5 has like 5 has some children like here, so 5 has another subtree with like a and b, so we don't have to keep all numbers, a and b. So instead of 5ab, it'll look at the very leftmost value, which is a, then 5, and then b, and then it'll continue. So even if it was like another value all the way down here, we follow that process of exploring the leftmost value when we have our root node. So our root node is now 5. So here it'd be like CA 5B. So now it continues this process. So this will explore the root subtree, set root to right to handle all right values. So if we're handling all left values, handle left values. And so if this is handling all the left values and this is handling all the right values, that's basically all there is to it, because tree only has left or right values, right? And we can say and root is not equal to null, or root is not equal to null. Because what if we have a case of like, so let's do this. We have 1, 2, and then we have 3. In this case, our stack is empty, but we still have 3 because we set it to root dot right. So that's why we need that second condition. I think that's it. Yeah, so that's pretty simple code. I hope I explained it kind of well. But, you know, like, looking at the solution and then being able to explain it like bit by bit, like why don't we use a queue instead of a stack? I think that's the important part, you know? You should really like drill down these problems. Hell yeah. Sweet, 100%. Type of like that. Oh, shoot, okay. We got some annoying problems, I'm sure. Oh, level order traversal. Okay, this is chill. Because I have a level order traversal logic pretty drilled down. Okay. Given the root, return a zigzag, level, or traversal. Just dumb it down for yourself, you know? So 3, 9, 20. First you need a level or traversal, and then you can reverse the lists. So let's make a function. Public list integer. Actually void. It could just be void. First list. I mean, you can have some boolean to decide how you add it later, but why make your life harder, you know? This is easy. Let's see. Left is equal to 0. Right is equal to input dot size. While left is less than right. And temp. Okay, temp is equal to input dot get left. Input dot get left. Input dot at. Input dot. How do you set value at index list Java dot set? Yeah. Input dot set left to input dot get right. Actually, I'm messing this up. Let's make the right the temp value. No. Left. I'm not messing this up. Left is the temp value, and then input dot set right to temp. List dot get Java. Yeah. Then we could do left plus plus, right minus minus, and we're good. Iterate our pointers. Okay, so now we have our reverse list. How do we get the level order traversal? Okay, think again. This is like another thinking exercise. What do we have? We have 3, 9, 20, and then 15 and 7. All right, so we want to do level order traversal. I explained this somewhere before, but the values that we want to see in a level order traversal are left to right. So we're not thinking about the zigzag yet, right? So if the level is the second level, we want to see 9, then 20. So if we have 3, we can push in root 3 dot left and then 3 dot right to some data structure, right? And then you can use, if you push in right and then left, you can use a different data structure. But since we're pushing in left first, and what's the first value we want to see? We want to see left first. So that means first in, first out. That implies a queue. Okay, so let's move this code down. This is important. So we want a queue of values. And then if root is double equal to null, just return output. Actually, it doesn't even matter. We just do if root is not equal to null, and add it to our queue. And our queue is list of pre-node queue to a new queue to add root. Okay. Now while not queue is empty. Alright, while it's not empty, what do we want to do? Oh, we can get the level size. So when we push in 3, we know the size is equal to 2 or just 1. So we push in 3 initially, right? we know the size equal to 1, right? Then we push in 9 and 20. Before we do any operations, we know the size of this level is equal to 2. Then we're going to do some operations like push in 9s left and right and push in 20s left and right, which are 15 and 7. So in the start of each for loop, we should get the size of the level. Okay, so and then we could just iterate through all the values in that level size. Which is if Q at and then we have to have a list for the current level. Cur level dot add Q Okay, so let's split up a little bit. Let's have our boolean should which one should we reverse? So it should be false and the next one should be true. So very first level is false. If should reverse output dot add reverse. Actually no, just reverse this cur level. Output to add cur level and should reverse is equal to not should reverse. Okay. Check your semicolons. Check your spelling. Oh yeah, and your final return. Let's see if I'm like that. Index 2 out of bounds for link 2. Oh my god, dude, I always make this mistake. Always make this mistake. Can't they do like input dot last index? I feel like that'd be a good, but just like nice to have, so you don't have to do dot size -1. Just give me a last index, please. Just give me a last index. Java was at 20. Dude, I want to see a last index. This is ridiculous, you know? Does Kotlin have it? Kotlin dot array dot last index. They have it. Oh my gosh, look at that. That's beautiful. That's why people use Kotlin. Java array last index. Oh yeah, last index of, I don't know what that is. Make it simple. Yeah, I don't want to use that, buddy. I don't want to use that. I'm talking to myself. Yeah, see, sometimes you gotta talk to yourself and pretend you're explaining the solution to somebody. Because it helps when you're doing the problems. But Dude, I freaking hate binary trees, man. I hate it. I hate it so much. Okay, this is pretty nice. This one's, I'll do this problem. Why? Because we just did a problem, which, believe it or not, is very, very related. So how are elements in a binary tree defined? The smallest is the leftmost value, then the root, then the right subtree, and then the root and the right subtree, and the root and the right subtree. What does that look like? Doesn't that look like an in-order traversal? A problem we just did? They really try to drill down certain concepts with these playlists. And we're going to do the fancy in-order traversal we got. And all we're going to do is, instead of a list of an integer, we're just going to return an int, which is return output dot get k, and we're going to pass in an int k. We're going to run iter k smallest and root k. Return it. Let's see if it runs. Zero indexed. So if it wants the first smallest, it really wants array at 0. Look at that. Accepted. Yeah, look at this guy. He just does an in-order traversal, but it's recursive, and it doesn't have to save the values. Mine's iterative, man. Technically better because you can always have that array. You can reference what's the nth smallest, what's the kth smallest. His is better because I think what he's doing is he's not exploring the entire tree. Well, actually, he is. Count minus minus. Yeah, no. He's not exploring the entire tree because once he finds the element, he stops. So that's why his is actually faster. Mine explores the entire tree so you can get the full traversal. Alright. Hey, you know, it still works though. It still works. That's what matters. Let's do another one real quick. Damn, Leetcode's kind of slow. Okay. Populating next right pointers. Two children, blah blah blah. Okay, so let's do some recursive solution where we pass in two nodes and we connect them. Whoa, this is important. We just don't have left and right anymore. We have next. Oh, that's the one we want to populate. Okay. Node A and node B. Okay, so initially we want to send in. What do we want returned? We're all. Okay, so we just want to make this void and then we return the parent, I'm guessing. So if want to do, we want to connect to root.left and root.right. Okay, so we can connect, hey, root.a.next equal to b. And then what do we want to connect? We want to connect to, actually we could just make this if a is double equal to null or b double equal to null. Just return. So we don't have to do these checks. We just need to check here if root is double equal to null. Okay, a.next is equal to b.next. Connect to a.left and a.right. Connect to a.right to b.left. Connect to a.b.left to b.right. Okay, so let's throw up the example. 1, 2, 3, 4, 5, 6, 7. I see. So we connect to the first values we're passing is 2.3, so we connect 2 to 3, and we call in 4 and 5. So we connect 4 to 5. And we call in 5, 6. Connect 5 to 6. And we call in 6, 7. So we connect 6 to 7. What we really want to see is, so these are all tabbed because they're like part of the subtree, is does it work another level down? If it works another level down, it's probably solid. Let's call this A, B, C, D, E, F, G, H. So for 4, what do you call? You call A comma B, B comma C, C comma D. Okay, yeah, it works. C comma D. And wait, 5 to 6. Oh, because we have that linkage. It's like the same pattern. So we connect, for 5 to 6, we connect C comma D is already connected. We connect D comma E, which is a new one, and we connect E comma F. So we do actually double up on connections, but that's okay. You know, it's not actually doubling up, right? It's just like resetting the value to the same thing. Expected 1 to 2 to 4. Okay, 1. Dude, I hate these test cases. You can't see output properly. Okay, I passed that one. 1, 2, 2 to 3. Your function should populate each next pointer to the point on the right node, just like in the figure B. What are we missing here? Oh, we don't connect B dot right. B dot right to B dot next dot left. So b dot next dot left. So b dot right, I think what we're missing here is a and b. We do a dot right is equal to b dot left. No, b dot left. A dot right is equal to whatever our b is. Instead of b, let's just do. No, b dot left is fine. A dot next dot left. Equal to b. Oh, a dot next is equal to b. Just b by itself. Without screwing this up. Let's run it. Yeah, that was screwing us up. Okay. Sweet. Sweet, 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 sweet. Sweet, 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 sweet. Okay, yeah. So that's why we did the 3 levels, and we show it always works out. And then there's some like duplicates, like CD here and CD here and EF here and EF and somewhere down here. What was messing up was this right there. Okay, cool, 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 cool. How many questions do we have till I can take a break? We have 2 more. Let's do number of islands. I want to leave construct binary tree from whatever, because I have a bad feeling this one's going to be a hard one. From pre-order and in-order traversal. Yeah. Okay, so if you don't know depth first search, it's an extreme. All these concepts are easy to understand. People say it. They're really easy. People say like they're like so impressive. Oh, it's a depth first search solution. No, dude, just use your logic. In this solution, you get a whole bunch of 1s and 0s. So we want to count the number of islands, which is a group of 1s. So as soon as you see a 1, go find all the other 1s and set them to 0, and just increase your count, right? So it makes a lot of sense. Let's do bound checks. Oh, we're dealing with characters, so yeah, these single quotes. So with these bound checks, it's a lot easier because you don't have to. You can pass in whatever values you want, and it'll check it for you. So you don't have to like do like a whole bunch of meticulous tests. Like, hey, is our left value gonna go to left? Is our right value gonna go to right? So some examples would be if r is greater than 0. then do this, blah blah blah. But this is just one clean check in one space before you do any code. Check the balance. It's a lot cleaner. So now I can do stuff like DFS, grid, row +1, column. I can just pass in whatever I want. But row -1 in column. So this is checking the 4 sides. Do diagonals count? Do diagonals count? Is any diagonals here? I don't think they count. Yeah, we're connecting adjacent horizontally or vertically, not diagonally. Stack Overflow, damn. That means that we are doing something recursively for infinite time. Let's see. Oh yeah, so of course we gotta set it 0 first. Because it's gonna like jump this way and this one's gonna jump this way and it'll be like a back and forth loop. Alright, easy question, intro to DFS. Alright, last question and then I'm gonna go take a break. And I'm out of water. Oh, damn. This guy's kind of jacked. This guy's got some puppies on him. Alright. Okay. Shoot. Hard problem. Order and order. So what is pre-order? It's root, left, right. And in order is left, root, right. So when I say left, I really mean left subtree. So the whole left subtree is there, and right is the right subtree. Okay, so if you look at pre-order, if it's always root, left, right, so it's gonna be root, and then root of first left subtree, and then root of the next left subtree, etc., etc. So you can always get the roots by the, so 3, 9, then 20, then 15 and 7. Yeah, so I guess what we can do is we can have one value, we call it like build tree help in order to be order blah blah blah. Let's have a variable to tell us which root are we at, or which root are we at in the pre-order. So pre-order root. So what do we want to do? So when we see, let's look at these examples. And this one. I guess you can't really make this not. Let's just make it a global variable or an object-based variable. So in this instance of this solution, it's not static. Static would be shared across all instances. So when we start, let's check pre-order root is equal to 0. So here, let's see, this is pre and this is in order. So we know the root is 3, right? So the first root is 3 from the in order. So we just make that x, and then we set this to x2. And with in order, we know it's root, left subtree, and right subtree. So we know that our left subtree is here, and our right subtree is whatever is on the other side. So 15, 27. So root, so we could call, and then the next value is the root of the left subtree because it's pre-order. So root, so when we break this down, root left, right, left subtree. So you plug it back into pre-order, so it's root of the left subtree, then whatever's left of that and whatever's right of that. So the next value we look at is 20, so we should call a function on our left subtree first. So it should be set root, call function on left, call function on right. So when we, these are three steps. Call function on right, call function on right. So 3. So we see the next value is 9. So 9. And we see there's no left subtree or no right subtree. So there's no more calling. So this, when there's like no left or right subtree, this ends the calls, right? So now you're looking at the right subtree. Next value is 20. So replace that with the x. And now you know your left subtree is, so we know this is 9. It's not really an array anymore. It's not a subtree anymore, it's just a node. So here we know our value is 20 now. And what is the left subtree and right subtree? 15 and 7. Okay, so so now we set the root again. We do the same process. We have root.left is equal to 15, so we explore the left, and 15 is, we set the node. So set 15 as node, and then root.left and right are null because the left array and the right array are empty. Then we just look at 7, we called it, so we're not doing any more left calls, we make a right call. So this is x, we added 15, and lastly we add 7. So we add 7 and we're done. So this would be a pretty good, easy solution if you could pass in the left subtree and the right subtree, but it's not really optimal in that way because then you're like recreating an array for every block. So we could just say, for in order, let's do int left start. So let's actually make these on new lines. Int left subtree a. So that's the int left subtree b, and then we have int right subtree. Yo, these are terrible names. Int left a are, let's see, left a, and then int left b, int right a, int right b. So this is the start and end of left subtree, and start end of right subtree. Or actually, we could just say start of subtree, start subtree, start A, and start B. So in our in order array, this will tell us what's our range of values. So initially it's the full range, and then we decide the left and subtree and the right subtree in the function. So let's do if pre-order, let's see, pre-end. pre-order index. If edge case pre-end double is greater than or equal, it's just equal to pre-order dot length return root, and we gotta pass the root, I guess. Return null, just return null actually. And then we want to make a root, so tree node root is equal to new tree node pre-order at pre-end. Now in order to find, we gotta find where the first value is in the array. So let's copy these back so you can see it again. Now could you do binary search to find that? Yeah, you could, but come on, we're just solving one problem at a time. Optimize with binary search. We could find this later. Int index found int is equal to 0, -1. For this is int I is equal to 0. Then pre-order dot length. They're both the same size. But we can make it in order. They're both the same size though. If in order dot get in order dot I so equal to root dot val found end is equal to I and break. So we assume this always works. Oh man, might as well make it clear. The assumption is this must always work if input is valid. So we could do if found in double equal to -1, throw an error, or we'll just print out error can't find index of pre-order value, and we can just return null. Okay, so now that we found the value for this must always work. This will always work. Okay, cool. Now that we found the index. Okay, we could set root dot left. Oh yeah, and also let's update pre-end because we want to look at a new index. Root dot left is equal to build tree help. Build is equal to build tree help. Pre-order in order start A to found in -1. And then root dot right start found in +1 with start. Let's just make start and end. I don't know how to do start A and start B. Start and end. Start and end. Okay, so for left subtree in the in order and explore right subtree. Because we have to do that in this way because we're using pre-order. If it was something like post order, we would explore the right first and then the left. Because I think post order would be like root, right, left. So if you are an interviewer and you really want to grill an interviewee, do post order because they'll show if they really understand how it works. Just simple variations. You can check if somebody's like BS and if they don't understand something. So return root. But again, we want to add some more conditions here. So if start is double equal to end, or start is greater than equal to end, return null. What if it's equal? Maybe not equal, because if it's equal, then that value might be valid still. Oh yeah, I didn't call anything. And also this is an issue. Build tree help. Turn. Build tree help. Pre-order. In order. Yo, man, it's not about who's listening. Yo, there's haters in your own family. It's about practicing. Think about it. Think about it. Literally think about it. If you're practicing talking your problems through, like your technical problems, that's what you do in an interview. You're just talking about your technical problem. I'm doing it live, bro. Oh my god, look at that. Easy, easy. I'm sick. I'm so sick with it. Am I sick with it? Oh, I'm sick with it. Yeah. I thought this problem was gonna be annoying, but it's not that bad. It's not that bad, and we never get the error case because that's impossible if you have valid input. Okay, so am I done? I'm not paying for premium. I'm not paying for premium. In order successor in binary search tree. Oh, I don't know what that means. Okay, we've done this. We'll do backtracking. I'm gonna go take like a break. Go watch some Instagram reels. You know how it goes. Alright, goes. Alright, bye.